Hey, welcome back. This is going to be the second video on my channel. It's following on from a classification video that I posted a few months back. I've been a bit distracted, had COVID, you know, did some things. It's been a while, but I'm keen to get back on it. Uh, I'm back with another Kaggle dataset that I'm going to be having a looking at because the last video explored a classification problem. I thought this time let's go through some linear regression. It's just going to be kind of in the same vein as last time, going through giving quite an organic approach to how I'd look at a problem like this. I don't think the model we're going to make is perfect. I don't think it's the very best you could squeeze out of it, but this is more just a video showing, how I'd approach it in an organic way. That's probably a repetition at this point, but just thought I'd give it a look. So for this video, what I've got is a personal cost data set. So you've got a medical data set, sorry. So I think there's an individual, certain like kind of features of that person. For example, I think it's what age they are, what sex they are, and where they're centered in the country. And then from that, you want to kind of derive how much they would cost for this medical procedure. I assume they're comparing against the same one, otherwise it'd be pretty pointless. But let's read that in, and we will go through it. And I think the biggest thing is that it's going to be very similar to the model development. It's going to be quite similar in terms of the data preparation for it. Any data or feature engineering we have to do will be quite similar, but I would say the model development will be using some different classes of algorithms, which will be interesting to go through. So at the moment, I'm just trying to make my initial imports. I like splitting my files up by by headers, just makes it a bit easier. You can also split this out into multiple files, but I don't really like doing that. So this is generally how I do it. So I'm going to import in the basics real quick. So generally going to use pandas because we're going to be storing everything in data frames. Use NumPy arrays because we're going to be able to use some of the numeric functions they have to clean our data up or even to replace values. Matplotlib to visualize it, and Seaborn is more of a specialized plotting library. It's built on top of Matplotlib, but I just kind of prefer the look of it. So that's kind of what I'm going to do. And there's some other bits and pieces that I can do to that we can utilize from the Seaborn package that makes I think the visualization is a bit nicer. So just for that at the moment, I have no idea what I've got. Okay, so it's called insurance.csv. Okay. Let's have a look at what this looks like. Okay, oh my god, this is tiny. Okay, so we've got the age, sex, BMI, number of children, I imagine that is, smoking, and the region, I imagine, of the country. So this is super basic. So I imagine off the bat, this is going to be a very simple problem to look at. What I do notice straight away about this, and I can confirm it with df.info, pretty sure it's user parentheses with that, yeah, is that we kind of want everything as this int64 as a float. Basically, we want it as a numeric because if we're going to, machine learning models will not accept something like a string or a character like this. It also will have to one-hot encode it or label encode it. It's looking like one-hot encoding is just going to be the easiest, if I'm completely honest. But okay, let's have a look. All right, so one thing I do kind of like to do is plot some of the variables beforehand before I start going into the nitty-gritty stuff. So one of the things I always try and do is have a look how at least the target variable that we're trying to predict is distributed. So what we're going to do is do sns dot, actually no, plt dot, let's see what happens. I like this one because it's so non-specific. Sometimes it comes back with stuff that you're looking for and sometimes not, but we'll have a look. So yeah, it's a bit all over this place, to be fair. Let's have a look. Yeah, okay, so it's got quite a long tail to it, so it's all right, but we're gonna see that immediately. I'd say we might have some problems with how this is distributed, because obviously it's so left-hand heavy here, closer to the 0. There might be a bit of a problem. So I think something we could investigate when we're looking at potentially the analysis stage and then also model development is trimming this off, and you can use kind of rules of thumb to do with interquartile ranges and how you would look at trimming off outliers. We can also use quite a good loss function called, as you can see, I've got it here already. So root mean squared, which is very sensitive to outliers. So we could utilize that, which would be useful. One way we can actually have a look about how many of these values are lying outside of like the upper quartile, as we're using a box plot. I think they're called whisker plots as well. Honestly, no clue. So we have SNS dot box plot. Let's have a look. Yeah, so we can see so much of this is kind of outside where we'd expect. So if we were going to make this cut, we'd probably do it around, call it 3.2. Use about 3.2 would be probably the one I'd do it. We can also import something like SciPy, Skippy. I can't remember what it's called. And that allows us to use something called a Z-score, which I think allows you to trim it by whether or not a value falls within 1 or 2 standard deviations, or 3, or whatever the threshold is you set it as. So that's something you can look into if you want, because this is quite a low key video and I'm not really going to go super in depth. I think I'm just going to make the cut about here. I'm going to call it 3,200 or so. We'll cut off all of these. So I imagine we might add, what will be useful is having a side-by-side comparison with the accuracy of the results from our model without removing these outlying values. Okay, so that's interesting. Okay, that's interesting. And you can also get a bit fancier with Seaborn, and you can look at how these values are affected by other variables within your data frame or within your data. So if you wanted to do an SNS.his plot again, we pass in df.charges, and then we want to do hue is equal to, we want to set it to see how it's different per sex. Oh dear. Oh dear, oh dear. The following variable can be assigned with wide form data. Hue. I have no idea what that means. What does that mean? Does it change if I encode it? That's the question. Mm. Mm-mm-mm. Let's have a look. Okay. Yeah, so this is what it should look like. When you already have data in a long format, you can specify the x values using x equals and the color. Oh, does it want you to do it like this? That's annoying. Okay, I think I know what that. So I think this is generally how Seaborn works, is that if you're using a plt.plot, all you can do is just pass in data you want to plot, and it kind of handles that for you. With Seaborn, what they like you to do is put in the data, so it's in your data container. So in this frame, in this case, it would be our df data frame. We then want to pass in our x equal to the name of the column that we want to look at. So in this case, it's going to be charges. And then we want to pass hue is equal to Yeah, there we go. Okay, that looks rubbish. How can I make this look a bit nicer? Dis plot? Oh, maybe that's what I need. Always learning. Ignore that. That was silly. Yikes! I don't know what I've done here. Oh, kind equals KDE. Haha. Got ya. Oh, I reckon that's gotta be a string. Yeah. I mean, better. Better. Fill is true. Okay, that'll be the one. God, I did not realize I had to pull so many teeth to get this working. Okay, there we go. So we can see generally that some of the more expensive treatments are found in male individuals. Interesting. And you can do this whatever you want. Like anything you're really kind of interested in. I imagine what we will see if we do something like compare smoking is that there's going to be a lot more expensive therapies that are going to be, oh goodness, could not, oh, smoking or smoker. Oops, sorry, that's me getting too trigger happy. Okay, so if you smoke, yep, you have on average probably a lot more expensive therapies as you could easily predict. So yeah, you can just have a bit of fun with that and see what happens. I actually kind of want to do region real quick just because I can. I want to see 4 different curves. Oh no, that'd be kind of fun. Oh my god. Wow. Okay. Southeast, you appear to be out of luck. Yeah, that's pretty cool. That's pretty cool. I actually think if we remove fill from this, that might actually make it look a bit nicer. Because we'll just see the actual curves themselves. Okay, that's pretty cool. Okay. All right, so there seems to be a sort of spike at around 4,000 euros or whatever for individuals from the southeast. Yeah, that's pretty cool. I like that. So I love doing stuff like this. It's fun. Okay. All right, I like that. I like that. Cool. That seems like a good one. So yeah, you can play around with these and get whatever you want really. I'm gonna go ahead because I don't need to present this obviously to anyone. You know, it's just showing some techniques that I would use personally to look through data. So I'm not going to go super in depth with them. What I'm going to do now is go on to some feature engineering, which is essentially to convert these strings, and then I want to check for some missing data as well. So let's do some of that. Okay, cool. Code heading, and then I'm going to go feature engineering. So I'm going to be it's kind of like both, I guess. Data cleaning plus feature engineering. Cool, that's fine. So I think the first thing we want to do is convert our data. So as I was talking about, there are kind of 2 approaches, and I think I did cover this in my last video. You can use one-hot encoding, or you can use label encoding. So one-hot encoding, I showed it briefly just now, is where essentially you split out target columns as such. I'll show you like this. So p.get dummies, and for example, one of the things that we'd need to convert would be the sex, as I think I did previously. So if we look at the sex column, you can see here that it will have male and female. But if it loads in time, we have male and female. So all it's doing here is it's splitting this one column, holding these 2 types into 2 columns, one for each type. Easy. So I'm talking about this a lot. So one of the reasons we want to use one-hot encoding as opposed to something like label encoding would be that label encoding would retain the one column, but just swap every instance, for example, of male to be equal to 1, or every instance of female equal to 0. And that would be fine. It would be all right. But it's usually best, and I'm going to forget what it's called. Sort of like, I think it's called ordinal categorical variables. But essentially, when you use when there's one column and there's 1 and 0, machine learning algorithms will assume there is a relationship between the two in terms of kind of a hierarchical relationship, whereas they're just, in this case, they're just different. They just represent different sexes. All you would need to do is to use label is one hot encoding for this. Sorry, if we had something where each value within this column were more related, for example, if one example I think is used quite a lot is like price ratings, for example. So low, medium, high. Medium is higher. Medium is closer to high than low is to high. So therefore, it would make sense to use a sort of encoding method that maintains this hierarchical relationship. So I hope I didn't absolutely bomb that explanation. I think you might have to scroll back, to be honest, but that's kind of why I'm going to use this approach. So all we're going to do differently is create something to hold all of our encoded variables. So for this, what we're going to do is pass in a list of the columns that we want converting. So it's going to be sex, smoker, and region. Okay. It's not going to find that now. Oh, God. Okay, and then we have a look at OHE. It's going to have all of our converted variables. Yep, there we go. We then want to drop these variables from our existing data frame because we're not going to double up on the information. We only want the one hot encoded version of the data. So we can do df equals df.drop. Oh my goodness. And we're going to pass in that same list. And you might notice here that I'm using one set of square brackets as opposed to two. And this is more about how you can get the list of column headers, I think, within a data frame. That's just kind of the pandas procedure, I guess. If you want to get into the nitty gritty of it, I do recommend going into potentially some of the docs. All I know is that for this, we only need to pass one set of brackets. But for getting this selection of columns, we need to get we need to get this double bracket. And I know that can be a bit confusing, but it's kind of, you just got to deal with it. It is confusing. So sex, smoker, and region. Then we have to pass in an argument axis equals 1. So axis equal the axis equal 1 means it looks from the top. If you didn't pass this argument, it would look in the rows. So this allows us to get to our so it actually finds the correct columns. So we dropped all the ones we don't want. We then want to merge this back in. So we have df equals df.merge. So merge is just we're going to introduce our data set, our one hot encoded data set back into our original one so we can still use it. So OHE, then we're going to have a look at df.head again. And essentially this will have our data ready. Oh, great. Is it join perhaps? Sorry, I might be getting ahead of myself. Yeah, it's join. So here we go. We've got all our data as we need it. Perfect. That's all we needed. Yeah, cool. So that's how we want our data looking. Now let's look if there are any if there's any missing data, and we can use Seaborn for this. And I usually write a function for this because I like checking more than once before and after a transformation, for example. So if we do def missing data, and you can do this visually and you can do this non-visually. It's up to you. I'm more a visual person, so I like doing it. So put in our figure parameters. So really kind of self-explanatory. The fig size is the size of the figure within the browser, and then the DPI is the dots per inches, so how sharp you want your image. And obviously, the higher the DPI, the longer it can take to load. We can create our fig variable, which will hold our plotting object. So the sns.heatmap. We'll have data.isNull. Data.isNull. and then we'll pass in our CMAP, which is our color argument. So for this, we're going to use Viridis. I like it, and it's one everyone has to do. It's a rite of passage, and we want to return our figure at the end. You don't have to put a return in potentially, but it's all good. Don't know why I put in that extra space there. So now we're going to call missing data. I bet this won't work. I remember actually we might have some problems with this. Oh no, perfect. Okay, we've got no missing data. Just to show you the less flashy way, to be honest, but it's not as fun. So we do missing data text. We don't need this. All we need is our return. We want to do our data dot is null dot sum over the length of our data times by 100. So you're just getting the percentage of missing data. So missing data text, and pass in df. Okay, we've got 0% missing data. Easy. Easy. So that means essentially we're good to go. I mean, obviously, I'm going to create another data set. I think actually one with the trimmed values that I was talking about a bit earlier, and I think I eyeballed it at like 3,000. 3,300. Okay, let's do that. So what we can do is it's really simple. So we're going to create data trimmed df is going to be equal to everything in what you call charges that's less than 3,200. And we're going to have a look at the size of that and then compare it to our original data frame. So that's only got 205 rows even, and our original has 1,300. Damn, that's quite a lot. I might bump that up a little bit. We'll have a look. Wow, there are a lot of people down that end. Oh well, we'll see how they perform next to each other. I don't really care. So let's do some model development. So. I'll mark down heading. Yep, thank you. Okay, so what we're going to do is more like my last time, the last video is I'm going to create a model, so a function even, so that I can kind of breeze through this a little bit. How are we doing for time? Breeze through this a little bit, so I just want to set our x and y's for our first, so it's going to be x and then y equal to df dot. Actually, no, we'll do it imports. What am I talking about? So honestly, you could time me doing this stuff. I could do a speed run. Linear, just to go through it really quickly. Import linear regression. And then we're going to do from sklearn dot ensemble, just so we have something to compare against. Going to use a random forest regressor. Oops, got the import from sklearn dot metrics import mean squared. Mean square or mean squared? That's going to be interesting. For some reason, my tab autocomplete is really slow. Mean squared error. Okay. Train test split. Our linear regression. Yeah, I think that should be fine. Pretty sure it should be. Whatever. So what we want to do is have our x equals our x is equal to df, and then we want to just drop our target variable that we're trying to predict. So in this case, it would be charges. df.drop, and it would be charges, and then give it an axis argument so it finds it. And then y is going to be the actual thing we're trying to predict. So df charges. Okay. And then we can mess around with this a bit later. And then we're going to call our train test split. And again, I'll have to wait because I can never remember. Can I? You can just go ahead and do it. Yeah, I'm too lazy to remember this. I really should know it by now. There we go. So set to 3 and then to 101, because that's just kind of how I learned it. That doesn't mean anything. Okay, now we're all set. And then we can do our def model development. So it's going to take our X train, our Y train, our X test, our Y test. So we got, actually, it's going to take our model first, even. Okay, that's fine. So we're going to have our linear regression is equal to model. We're going to do our lr.fit, and we're going to pass in our X train and our Y train. Love that. And then we're going to have our Y pred. It's going to be our predictions. Are going to be equal to lr.predict, and then it's going to be X test. And then we're going to print our mean squared error, and then we're going to do our NP, our square root, essentially, to get this root mean squared output. So mean squared error, and then I think we pass in our Y. Am I passing our Y test or my Y pred first? Oh, please help me. Oh no, I don't trust you. Y true and Y pred, yeah. Okay, so our Y true is our Y test, and then Y pred, and then print. I'm actually gonna make this a bit easier for myself. Oh my goodness. Okay, and then we can do mean squared. Oh my goodness, squared error is equal to this. Then we're gonna copy it again, and then do root mean squared error. So all we're going to do is wrap this in a square root. And again, going over this, I think the only reason we, oh god, I shouldn't do LR because I'm going to use multiple. I'll go. The only reason we're using the np.square root is that it's a bit more sensitive to outliers. So that's quite a good thing we should do. Okay, cool, I'm happy with that. Okay, so model development will now commence. So we're going to pass in our linear regression. We're going to pass in our these, basically. We've already created these variables locally. We're good to go. We're good to go. So we'll see if this crashes and burns, which it has. Name model is not defined. Where did I not change model? Oh, wait, what? Oh, that was supposed to stay as model. Sorry, my bad. Root mean squared error is 5,803. Okay, interesting. And then what I would like, so I believe that would be like, I'll show you how we can test this as well, about how accurate it is, like a more, so I believe that means it's off by $5,803, which isn't bad. Well, it is in that case. And this one, well, actually it's quite bad. Oof. Oh well, it happens. And then we're going to do the same thing, but we're going to use our random forest regressor. And these are generally, I find, to be better performing. So we'll see what happens. 4,009. Okay, so we do have an improvement, not a great one. So now we're going to try it with our trimmed data. Sorry, my headset just turned off. That was rude. So what we're going to do now is have our df trim trimmed DF. Sorry, I've completely forgotten. Oh no, they're not going to be exactly the same order. No. Cool. So you can see immediately, linear regression is smashing it. And this is our trim data sets. We've removed most of our outliers. Yeah, so this is obviously a massive improvement in performance. The one thing I would say is obviously when you're reducing the size of your training set, you are making yourself more prone to overfitting. So be very careful about that. We can see how these things are predicting in real time very, very, very easily. We just need to create basically this outside of the model real quick. So in this case, we would, what's our best one? Linear regression. So it'd be LR. Oh, it can still be algo. Sorry, my head is all over the shop. Okay, so we're actually going to call this outside of a function. So our algo is going to be linear regression. We're then going to fit it on our X train and our Y train as we did before. Let's wait for that to go. Our Y pred, instead of passing in our X test, we're going to pass in a list of values that we can actually see what the answer is. So if we go to DF trimmed DF even. Trim DF dot lock. And then basically, I'm going to get the first row, but put it as a. I can't bother with you. Trim DF dot lock. Whatever, don't care. So instead of passing in the X test, we want to pass in a list of values that basically we're just going to put in all of these values essentially. It's not going to be too bad. So if we put in 18, it's set for charges obviously because we can try and predict that. 33.770. Children 1 0 1 1. Oh god, 1 0 0 0. So, sorry, we can see basically that with because we've just put in this first row's information into here, we should see a charge similar to this. Well, at least we hope, right? 1694.17. Okay, and then we've got 1725. So that's not bad. It's not bad at all. And you can do this for every single row. This is basically just a way of going in, and it's also a validating kind of. I find it easy to do this, and I find that it's quite nice to actually see exactly these variables are going in, this value is coming out. I don't know, it just helps for me. I find it a bit easier. That's just me though, so that's essentially it. And this is also how you can apply new data to. You can save this model as a file now. You can call it into a new Python script or whatever, and then you can predict with it on new data that people can just put in. So that's one way you can actually kind of operationalize your model, which is quite helpful. So yeah, I think this is about it. I don't really know what else I can go from this. I think I kind of covered everything I was thinking of covering. Not that really there's a lot of thought that goes into these. Yeah, got our data in, done a bit of plotting, changed up the non-numeric data, plotted some of it again. We trimmed it. You can see that trimming here does actually increase our performance substantially, but leaves us more vulnerable to overfitting. So yeah, And then we've just shown an active example about how you can input new data into your fitted model and for it to create a prediction. So I think that's about it, to be honest. I don't have anything else I'd like to say. I hope you enjoyed it. I hope it was clear. I'm sorry I was rambling. I'm sorry that I'm so roundabout with these things. But yeah, if you enjoy it, please let me know. And if you'd like to see anything else in the future, also please do let me know. So yeah, have a good evening, and I'll see you later.